You are tuned to Iri-e-learning and I am your host, Teacher. In this structure and bonding lesson, we will illustrate ionic bonds using dot and cross diagrams. You can check the description box for links to all the lessons related to this unit. By the end of this lesson, we should be able to draw dot and cross diagrams to illustrate ionic bonding. If you have not yet done so, review the Unit 2 lesson on diagrammatic representation of atoms. The link is provided below. Let us do a quick recap on the electron configuration rules before we start our dot and cross drawings to illustrate our ionic bonds. These rules apply to the first 20 elements only. Recall that the first shell of an atom holds a maximum of 2 electrons. The second and third shell holds a maximum of 8 electrons each. The fourth shell holds a maximum of 32 electrons. And the lower energy levels must be filled first before filling the next energy level. We can now begin drawing dot and cross diagrams to illustrate ionic bonds. Dot and cross diagrams are simple diagrams that use a dot and a cross to differentiate the electrons of the metal and non-metal. It is important to know that, in reality, the electrons do not look different for each type of atom. Using two different symbols for the electrons in the illustrations make it easier to show the transfer of electrons from one atom, which is the metal, to the non-metal. So in this section, we will illustrate 4 examples of ionic bonding. Example 1, sodium fluoride. The first step involves identifying the atoms involved in the ionic bond to form sodium fluoride. From the name of the compound, sodium is one atom in the bond and sodium is the metal. So we can write the name sodium there. Fluoride indicates that the non-metal atom is fluorine. When you see a chemical name ends with the suffix "ide", I-D-E, that tells you it was the atom. So fluoride means that the fluorine atom had bonded with the sodium atom. So the atoms involved in this ionic bond to form sodium fluoride are sodium and fluorine. Step 2, we will record the symbols and the electron configurations for the atoms. If you don't know this information offhand, we can use the periodic table to help us. So let's take a quick look at the periodic table. Recall from the lessons in the previous unit that elements in the periodic table are arranged in columns called groups and rows called periods. The period number tells the number of shells the atoms have within that row, while the group number tells the number of electrons on the last shell of the atoms within the group, with the exception of group 0. Now, the atoms of the elements in group 0 all contain their maximum number of electrons and as a result are rarely involved in any chemical reactions. So we are not considering group 0 for this activity. So we need to find the symbol and electron configuration for sodium and fluorine. The symbol for sodium is Na. Sodium is located in period 3 and group 1. Therefore, sodium has 3 shells because it's in period 3 and 1 electron on that third and last shell. Since there is a third shell with 1 electron on it, it means that the first and second shell contains their maximum number of electrons. Consequently, the electron configuration for sodium is 281. A maximum of 2 electrons on the first shell, a maximum of 8 electrons on the second, and the third shell having only 1 electron because sodium is in group 1. Fluorine has the symbol F. It is found in period 2 and group 7. Therefore, fluorine has 2 shells, and on that second and last shell, there are 7 electrons, which means that the first shell contains its maximum of 2 electrons. Consequently, the electron configuration for fluorine is 2, 7. We complete step 2 by recording the symbol and electron configuration for sodium and fluorine. Step 3, draw the atoms involved in bonding and show the electron transfer during the ionic bond formation. We start with drawing sodium, its central nucleus, surrounded by 3 shells. We are using dots to represent the electrons on the sodium atom. So there are 2 electrons on the first shell, 8 on the second shell, and 1 electron on the third and final shell. Therefore, sodium, having just 1 electron on its last shell, will donate that 1 electron to fluorine. Next, we draw the fluorine atom, starting with the central nucleus, surrounded by 2 shells. Crosses are used to represent the electrons on the fluorine atom. The first shell has a maximum of 2 electrons, and the second, which is the final shell, has 7 electrons. Note that the last shell of fluorine, which is the second shell, can hold up to 8 electrons. Therefore, it requires only 1 more electron in order to become stable. Therefore, fluorine will accept 1 electron from sodium. Consequently, the valence electron of sodium is transferred to the valence or the outer shell of the fluorine atom. After sodium transfers its electron to fluorine, the third shell no longer exists because there are no electrons on that shell. At this point, sodium is no longer an atom, but a cation with 2 shells containing their maximum number of electrons. Since sodium atom lost only 1 electron, the charge is 1 positive. And the symbol we use to represent the sodium ion or the sodium cation is Na plus sign plus their meaning 1 positive. And the stable electron configuration for the sodium ion is 2,8. After fluorine accepts the 1 electron from sodium, it is no longer an atom but an anion with a charge of 1 negative. The fluorine ion is called fluoride and its symbol is F minus or F negative. Fluoride has 2 shells containing the maximum number of electrons. Therefore, the stable electron configuration for fluoride is 2,8. Now for the final step, step 4, the electrostatic force of attraction pulls the oppositely charged ions together. The electrostatic force of attraction is the ionic bond, which is very strong. So we have 1 sodium cation having a charge of positive, and we have 1 fluoride ion having a charge of negative. Note that the charges cancel each other. That is, 1 positive cancels 1 negative, giving the compound a total charge of 0. Therefore, we write the chemical formula of sodium fluoride as NaF. The second example is calcium oxide. We start with identifying the atoms involved in the ionic bond. The metal, which is always stated first in the name of the ionic compound, in this case is calcium. The nonmetal is oxygen. The oxide ion comes from the atom oxygen. Step 2, record the symbols and electron configurations of the atoms involved in the ionic bond. We will get this information from the periodic table. Calcium has the chemical symbol Ca. Calcium is located in period 4 and in group 2. Therefore, calcium has 4 shells because it's in period 4, and on that 4th and last shell there are 2 electrons. Since calcium has a 4th shell, it means the 1st, 2nd, and 3rd shells contain their maximum number of electrons. Consequently, the electron configuration for calcium is 2882. The first 3 shells containing their maximum number of electrons, and the last shell, which is a 4th shell, has only 2 electrons because calcium is in group 2. Oxygen has a symbol O. It's located in period 2 and group 6. Therefore, oxygen has 2 shells with 6 electrons on the last shell. Consequently, the electron configuration for oxygen is 2,6. 2 electrons maximum on the first shell, and the second shell, which is the last shell, has 6 electrons because oxygen is in group 6. We can now complete step 2 by recording the symbol and the electron configuration for calcium and oxygen. Step 3, draw the atoms involved in bonding and show the electron transfer during the ionic bond formation. We'll start with the calcium atom. We draw its central nucleus surrounded by 4 shells. Dots are used to represent the electrons on the calcium atom. So there are 2 electrons on the first shell, 8 electrons on the second and third shells, and 2 electrons on the fourth shell. Therefore, calcium will donate its 2 valence electrons to oxygen. Next is the oxygen atom, starting with its central nucleus surrounded by 2 shells. We're going to use crosses to represent the electrons on the oxygen atom. The first shell carries 2 electrons and the second shell carries 6 electrons. Note that the last shell of oxygen required 2 more electrons to make the maximum of 8 electrons on the last shell. Therefore, oxygen will accept 2 electrons from calcium. Consequently, the 2 valence electrons of calcium are transferred to the last shell of the oxygen atom. Take note that the fourth shell of the calcium no longer exists after the atom loses the 2 valence electrons because there are no electrons on that shell. After losing the 2 outer electrons, calcium is no longer an atom but a cation with a charge of 2 positive, 1 positive charge for each electron lost. The symbol for the calcium ion is Ca, 2 positive, and the stable electron configuration of the calcium ion is 288. All 3 shells remaining on the calcium have their maximum number of electrons. When the oxygen atom accepts the 2 electrons from calcium, it is no longer an atom but an anion with a charge of 2 negative, 1 negative charge for each electron gained. The symbol for the oxide ion is O, 2 negative, and the stable electron configuration of oxide is 2,8. Step 4, the electrostatic force of attraction pulls the oppositely charged ions together. The electrostatic force of attraction is the ionic bond, which is very strong. So we have 1 calcium ion, which has a 2 positive charge, and we have 1 oxide anion, which has a 2 negative charge. Note that the 2 positive cancels the 2 negative charge, giving the compound a total charge of 0. Therefore, the chemical formula for calcium oxide is CaO. 1 calcium, 1 oxygen. The third example is magnesium chloride. Step 1, we will identify the atoms involved in the ionic bond. As we know, when we have the name of an ionic compound, the first part of the name tells the name of the metal, so our metal is magnesium, and the second part of the name tells the nonmetal. And since it was chloride, we know that if it ends with "ide," it's coming from the atom, so we can look at our periodic table to see which element begins with chlor, CHLOR, and that would be chlorine. So our nonmetal atom is chlorine. Step 2, we will record the symbols and the electron configuration of the atoms involved in the ionic bond. We will get this information from the periodic table. So the metal magnesium has a symbol Mg, and it's found in period 3, which means it has 3 shells. And on the third shell, which is the last shell, there are 2 electrons because magnesium is in group 2. If magnesium has 3 shells with 2 electrons on that third shell, then the first and the second shell contain their maximum number of electrons. Consequently, the electron configuration for magnesium becomes 282. Maximum of 2 on the first shell, a maximum of 8 on the second shell, and 2 on the last shell because magnesium is in group 2. Next is chlorine. The chemical symbol for chlorine is Cl. Chlorine is also in period 3, which means it has 3 shells. First and second shell having their maximum number of electrons, and that third and last shell will have 7 electrons because chlorine is in group 7. Consequently, the electron configuration for chlorine is 287. We can now complete step 2 by recording the symbols and the electron configuration for magnesium and chlorine. Step 3, draw the atoms involved in the bond and show the electron transfer during the ionic bond formation. We start by drawing the metal atom, which is magnesium. We have the central nucleus surrounded by 3 shells. We're going to use dots to represent the electrons on the magnesium atom. So we'll have 2 electrons on the first shell, 8 on the second shell, and 2 on the last shell. As we know, in an ionic bond, the metal donates the number of electrons on its last shell to the nonmetal atom. So magnesium in this case will donate its 2 valence electrons to chlorine. Chlorine also having a nucleus surrounded by 3 shells. The first shell having a maximum of 2, second having a maximum of 8, and the third shell, which is its last shell, has a total of 7 electrons, which means that chlorine only needs 1 more electron to make a maximum of 8 electrons on the last shell, and it will get that 1 electron from magnesium. Now, after magnesium has given its 1 electron to chlorine, notice that magnesium still has 1 electron remaining to donate to a chlorine atom. So as a result, we have to draw another chlorine atom, and we donate that second electron to the second chlorine atom. Note that the third shell of magnesium no longer exists after losing the 2 valence electrons because magnesium has no electrons on that third shell. At this point, magnesium is no longer an atom but a cation with a charge of 2 positive, 1 positive charge for each electron that it lost or transferred to the chlorine atoms. The symbol for the magnesium ion is Mg, 2 plus or 2 positive, and the stable electron configuration for the magnesium ion is 2, 8 because it has only 2 shells remaining with their maximum number of electrons, 2 on the first, 8 on the second. Now, since each chlorine atom accepted 1 electron from the magnesium, therefore the chloride ions formed will each have 1 negative charge. The first chlorine accepted only 1 electron, so it gets 1 negative charge for the 1 electron it accepted. The second chlorine accepted only 1 electron from the magnesium, so it has a 1 negative charge for the 1 electron that it gained. So the symbol for the chloride ion is Cl- because each chloride has only 1 electron that it gains. And the stable electron configuration for chloride is 288. That is, we are giving the information for just 1 of the chloride ions. And for the final step, step 4, we're going to show the electrostatic force of attraction that pulls the oppositely charged ions together. Remember that the electrostatic force of attraction is the ionic bond, which is very strong. So what we have is 1 magnesium cation having a 2 positive charge, bonding to 2 chloride ions, 1, 2 chloride ions, each having a negative charge. So the overall charge on the chloride is 2 negatives, 1 here, 1 here. So the total of 2 negative charges on the chloride ions will cancel out the 2 positive charge on the magnesium ion. As a result, you form a compound that has an overall charge of 0 or having no charge. And so the chemical formula for magnesium chloride becomes MgCl2. Note we can summarize the final ionic drawing by drawing 1 chloride ion and putting 2 in front of it. We are now at the final illustration for ionic bonding in this lesson. We will be looking at aluminium oxide. The first step, as usual, is to identify the atoms involved in the ionic bond. We know the name of the ionic compound starts with the name of the metal, so we know our metal is aluminium, and oxide would come from the element oxygen. So our next atom is oxygen. Step 2, we will record the symbols and electron configurations for the atoms involved. We will look at the periodic table to get that information. Aluminium, symbol Al, is in period 3, therefore it has 3 shells. The third shell, being the last shell, will have 3 electrons on it, and the first and the second shell will contain their maximum number of electrons. Consequently, the electron configuration for aluminium is 2, 8, 3. 2 maximum on the first shell, 8 is the maximum electrons on the second shell, and the third shell having 3 electrons because aluminium is in group 3. Oxygen, symbol O, is in period 2, therefore it has 2 shells. The second shell, being the last shell, will contain 6 electrons because oxygen is in group 6. And the first shell will hold its maximum of 2 electrons. Consequently, the electron configuration for oxygen is 2, 6. We complete step 2 by recording the symbols and electron configurations for aluminium and oxygen. Step 3, here we will draw the atoms involved in the bonding and transfer the electrons during the ionic bond formation. Starting with aluminium, we have the nucleus surrounded by 3 shells. First shell having 2 electrons, the second having 8, and the third shell, which is the last shell, contain 3 electrons. We do the same for oxygen. We have the nucleus for oxygen, the first shell having 2 electrons, the second shell carrying 6 electrons. So therefore, we can see because aluminium has 3 electrons on the last shell, it will donate all 3 electrons to oxygen. However, oxygen has 6 electrons on the last shell and require only 2 electrons on that shell to complete the 8 electrons maximum on that second shell. So after aluminium has transferred the 2 electrons, there is still 1 electron remaining. And remember, in aluminium oxide, aluminium can only donate electrons to oxygen. Therefore, we draw another oxygen atom. This oxygen atom can accept 2 electrons to make the complete of 8 electrons maximum on that second shell. So it gets only the remaining 1 from aluminium, and it still needs a second electron to complete the 8. And remember, oxygen can only get electrons from aluminium in the aluminium oxide bond. Therefore, it means we have to draw another aluminium atom, and from that atom we donate 1 electron to that second oxygen. Now, the second aluminium has 2 electrons remaining on that last shell, and it has to donate those electrons to another oxygen atom. So we draw a third oxygen atom. It has 6 electrons on the last shell. Therefore, it needs 2 electrons to make the 8 maximum on that last shell, and it gets the 2 electrons from aluminium. As we know, aluminium would no longer be an atom after losing its valence electrons. So each aluminium lost 3 valence electrons. Therefore, it obtains a charge of 3 positive, and the aluminium ion is written as Al3+. And of course, the stable electron configuration for the aluminium ion is now 2,8. So for oxygen, we know oxygen is no longer the oxygen atom, but now the ion, which is called oxide, which is denoted as O2 negative. The charge on each oxide is 2 negative because each oxide gained or accepted 2 electrons. Therefore, the stable electron configuration for each oxide is now 2,8. That brings us to the fourth and final step, where the electrostatic force of attraction between the oppositely charged ions pull them together. And remember, that electrostatic force that pulls the ions together or causes them to attract is the ionic bond, which is very strong. So what we have now are 2 aluminium ions, each having a charge of 3 positive, and 3 oxide ions, each having a charge of 2 negative. So the total positive side would be 6 positives, and we have 2 negative, 2 negative, 2 negative, which gives a total of 6 negatives. So the total 6 positives cancel out with the total 6 negatives, and as a result, we form a compound that has an overall 0 charge, and so we can put the formula of aluminium oxide as Al2O3 because the bond involved 2 aluminium atoms donating electrons to 3 oxygen atoms. Note that we can summarize the final ionic drawing for aluminium oxide by drawing only one aluminium ion and making a note that there were two of them by putting 2 times or just the numeral 2 in front of the drawing of the aluminium ion. And we do the same for the oxide. Instead of redrawing all 3 oxide ions, we draw one oxide ion and make a note in front of the diagram that it's times 3, or we can just write the numeral 3. So that's it for a lesson illustrating ionic bonding using dot and cross diagrams. So we go into our lesson summary. Ionic bonds only occur between metal and nonmetal atoms. An ionic bond involves the transfer of valence electrons from a metal atom to the valence shell of a nonmetal atom. And valence just simply means the outer electrons or the outer shell. Cations are formed when metal atoms lose electrons. Anions are formed when nonmetal atoms gain electrons. The electrostatic force of attraction between oppositely charged ions is the ionic bond. Ionic bonds are very strong. It's quiz time. You have 5 seconds to answer each question after it is read aloud. Question 1. Which 2 atoms will form an ionic bond? A. Copper and zinc. B. Nitrogen and oxygen. C. Sodium and oxygen. D. Silicon and oxygen. The answer is C, sodium and oxygen. Recall that ionic bonds are formed between metal and nonmetal atoms, and the only option that gives the name of a metal and a nonmetal is C. Question 2. What would be the name of the ionic compound formed between calcium and sulfur? A. Calcium sulfate. B. Calcium sulfide. C. Calcium sulfur. D. Calcium sulfite. The answer is B, calcium sulfide. Question 3. What type of elements are involved in ionic bonds? A. Metals and inert gases. B. Metals and nonmetals. C. Metals only. D. Nonmetals only. The answer is B, metals and nonmetals. Question 4. Potassium, chemical symbol K, has the electron configuration of 2881, and oxygen, chemical symbol O, has an electron configuration of 26. State the name and chemical formula for this ionic compound. A. Potassium oxide, K2O. B. Potassium oxalate, K2O. C. Potassium oxide, KO2. D. Potassium oxide, KO6. The answer is A, potassium oxide, chemical symbol K2O. Using the electron configurations for potassium and oxygen, we can determine how many of each atom is required for the ionic bond. As we can see, oxygen requires 2 more electrons to make the maximum of 8 on its last shell, and potassium only has 1 electron to donate to oxygen. So therefore, we would require 2 atoms of potassium in order to get 2 electrons to donate to an oxygen atom. Therefore, the chemical formula for potassium oxide is K2O. 2 potassiums bonding to 1 oxygen. Question 5. Lithium, electron configuration 2,1, forms an ionic bond with fluorine, electron configuration 2,7. Identify the diagram that correctly shows the ionic unit formed. Is it options A, B, C, or D? The answer is D. As we can see from the electron configuration, lithium has 1 electron on the last shell, so it needs to give up or donate that 1 electron. So therefore, lithium can only obtain a positive charge after giving up 1 electron. Then fluorine, having 7 electrons on the last shell, will need only 1 more electron to make 8 maximum on that second shell. Therefore, fluorine can only accept 1 electron, which means that the charge on the fluoride ion is negative. We have reached the end of our lesson. If you found this video helpful, remember to like, share, and subscribe. When you subscribe, you will receive notifications as new videos are uploaded. So until next time, I am Teacher with Iri-e-learning.